Welcome to this lesson. Our topic is electrostatics and the subunit is called electric potential energy. We are going to study and embark on only numerical examples in this lesson, how we can calculate the electric potential energy due to charges. The first example reads, how much energy does an electric field do in moving a negative 7.7 microcoulomb charge from ground to a point whose potential is positive 65 volts higher? So we recall that the work done is equal to the work done by an electric field on a charge is the same as that charge which is being moved multiplied by the potential difference between the initial and the final point where the charge is moved. So the work that is going to be done here is going to be the charge, which is negative 7.7 micro, that's 10 to the negative 6, multiplied by the difference in potential. The charge was moved from the ground where the potential is 0, so it's 0 minus 65. 65 is the potential for the last point where the charge is moved, and if we feed in our calculator, we shall get 5.0 times 10 to the power negative 4 joules of energy. Example 2 says, how much work does an electric field do in moving a proton from a point at a potential of positive 125 volts to a point which is negative 45 volts? The continuation of the question says, express your answer in both joules and electron volts. So let's first see the first part. We want to find the work done by an electric field on a charge. Of course, in this case, it's a particle, but the particle is charged, so it's a proton. We know that charge of a proton, let's say that the charge is denoted with Q. So QP, or charge of a proton, is a positive E, 1E. Remember, that's going to be positive 1.6 times 10 to the power negative 19 coulombs. And the question wants work done, so let's say that the work done is denoted with W. It's going to be the same as the charge, in this case the charge of a proton multiplied by the potential difference between the 2 points where the proton moves. So remember, according to the question, the proton is moved from a point whose potential is 125 volts to another point whose potential is 45 volts. Therefore, here now the work done is going to be the charge of a proton, which is 1.6 times 10 to the power negative 19, then multiplied by the difference in potential is going to be 125 minus negative 45. Then the work done is going to give us where we shall get a 2.72 times 10 to the power negative times 10 to the power negative 17 joules of energy. Remember, work done, you can, the potential difference, even depending on where the charge is moved to where it ends, the potential difference may be positive or negative. According to the question, we have already covered the answer in joules. Let's see the answer in electron volts. Work again is going to be the same as the work done in joules. Well, remember that 1 electron volt is 1.6 times 10 to the power negative 19 joules. So that means that 2.72 times 10 to the power negative 17 joules will equal to 2.72 times 10 to the power negative 17 divided by 1.6 times 10 to the power negative 19, and the answer is in electron volts. Of course, the work now is going to be, if you feed in your calculator, you get 170 electron volts. Well, let's see the next example. It reads, a 35 microcoulomb charge is placed 32 centimeters from an identical positive 35 microcoulomb charge. How much work would be required to move a positive 0.50 microcoulomb test charge from a point midway between a point which is 12 centimeters closer to either of the charges? The 2.5 joules is the answer. Let's see whether we come up to this. But before we go into the details of the answer, let's interpret the question on diagram here. I've assumed that the charges are placed at points A and B, and that charge is identical to the other one at B. It's 32, it's 35. It's 35 microcoulomb, not 32. This is 35 and that's 35 microcoulomb. Then they are saying that there's a test charge of 0.5 microcoulomb midway. If it is midway, it is at point O, where point O now is going to be 16 centimeters either way, 16 centimeters from A and 16 centimeters from B. Then this charge is moved to point C according to the illustration, and they're saying it is moved 12 centimeters closer to either of the charges. So if it is moved 12 centimeters to point C, from O to C. Well, let's see what happens next here. To find the work done, we have to remember that work done is the same as the charge that is being moved multiplied by the potential difference between those 2 points where the charge moves. So therefore, this is going to be the charge multiplied by, so since the charge is moved from O to C, means the work done by the field is going to be the charge that is being moved multiplied by PD is going to be VO minus VC. So meaning we need to look for VO. Okay, so VO is going to be due to the charge placed at A and due to the charge placed at B. Therefore, it's going to be VA plus VB. If you wish, you would say it is VOA plus VOB plus VOB. This is going to be, you can see that the charges are the same. So following the formula for potential as KQ over R, the charges are the same and the K is going to be the same. So for simplicity, that's going to be KQ divided by 1 over R plus 1 over R. So it's the same distance. A is the same distance from O as B, so I call them R, all of them are R. Then VO is going to be the same as K, which is 9 times 10 to the power 9 multiplied by the charge, which is 35. Well, that is 35 micro times 10 to the power negative 6 multiplied by 1 over R plus 1 over R. That's going to be 2 over R, but R is 16 centimeters, so that's 16 times 10 to the power negative 2 in meters. So VO, feed in your calculator, you're going to get 3.94 times 10 to the power 6 volts. Let's go ahead and get VQ, VC, VC. V at C, the potential when now the charge which was at O is put at C. Almost the same thing is going to happen. It's the same as V at C due to A plus V at C due to B. So V at C is going to be these points A and C, A and B have the same charge. Therefore, it's going to be KQ bracket K. So C from A to C is going to be 1 over, from A to C is going to be 16 plus 12. 16 plus 12. Then plus 1 over, the charge is at C, so from C to B, if from A to B is 32, and then this is 16 plus 12, that's 28, then this remaining here is going to be 4 centimeters. That's 4 centimeters, that's 4. So VC, if you feed in your calculator very well, you're going to get 9 times 10 to the power 6 volts. Times 10 to the power 6 volts. So we are looking for VOC, which we said is VO minus VC. We already have VO as this, we have VC as this. If we substitute, because of space, get the difference between these two. 9 times 10 power 6 volts minus 3.94 times 10 power 6 volts. You're going to come up with 5.06 times 10 to power 6 volts. That's going to be the potential difference between those 2 points where the charge is moved. Consequently, we are looking for how much work would be done. So how much work, let's say that work is W. We have already seen up here that work is Q times PD. The charge which is being moved between those 2 points is 0.5. So that's 0.5 microcoulomb, which is times 10 to the power negative 6. This one is multiplied by the potential difference between the 2 points where that charge is moved. So the potential difference is 5.06 times 10 to the power 6 volts. And if you use your calculator, you're going to come up with 2.53 joules of energy. You must be careful here is that the potential at O is created by the charges placed at A and B. The potential at C is also created by the charges placed at A and C. So if a charge is moved from O to C, you need to get the potential when the charge was you need to get the potential at O, and then get the potential at C, and then get the difference between those two potentials. So that will be the PD. And then that means if a test charge is moved from O to C, then the work that is required to move that charge would be the charge which is being moved multiplied by the potential difference between those 2 points. Having seen how we can calculate the potential energy or the electric potential energy from the previous examples, here comes the exercise for you. It reads 2 point charges, so positive 5 microcoulomb and negative 3 microcoulomb are placed at points A and B as shown below in the diagram. Distances OA and OB are 900 millimeters and PO is 1200 millimeters. Calculate the work done in moving a charge of negative 3 microcoulomb between points P and Q. You have to know that your distances AO is given as 900 millimeters, and distance OB is also 900 millimeters. Change it to meters, and the distance of PO is also 1200 millimeters. Change it to meters. You must remember also that the potential, you have to calculate the potential at, since we want to find, the question wants you to get the potential between P and Q. Call it VPQ, which is VP minus VQ. So go ahead and find VP at first. VP is going to be the potential. V at P is due to the charge placed at A and the charge at B. So it's going to be V at P due to A plus V at P due to B. Go ahead and find VQ, which is going to be V at Q due to A plus V at Q due to B. Then after computing this and computing this, feed them in this equation here. Let's say that's equation 1. Go ahead and get the difference. Then therefore the work done that is needed is going to be equal to the potential difference, or it will be the charge which is being moved. In this case, the charge is negative 3 microcoulomb multiplied by the potential difference, which is going to be Vp minus Vq. Then you'll be having the answer.